Assalamualaikum and a very good morning. Today, we are from CEEC110-4E2 would like to present our topic, which is incorporating fiber waste in sustainable concrete, a study on fiberglass. Our team members are first, Natalia Sierra, Nur Dahlia, which is me, and lastly, Shafi Aina. Our presentation outlines would be introduction, secondly, methodology, third, findings, next, discussion, and then conclusion, and lastly, reference.
Introduction. Fiberglass, also known as glass reinforced plastic, is made from glass fibers flattened into sheets, arranged randomly or woven into fabric. It is a strong, lightweight, and flexible material widely used in various applications like bathtubs, boats, and aircraft. Combined with resin, fiberglass forms a durable composite, making it ideal for construction. There are few research questions. Number 1. How does fiberglass waste impact the strength and durability of concrete? 2. What are the environmental benefits of using fiberglass waste in concrete production? Number 3. How can fiberglass reinforced concrete be implemented in the Malaysian construction industry? The objectives of our project is to evaluate the mechanical properties of concrete with fiberglass waste additives. The second one, assess the environmental impact of fiberglass reinforced versus traditional concrete. And the last one is to recommend practical applications of fiberglass reinforced concrete in Malaysian construction projects.
For the methodology, for step 1, batching. In the initial stage of glass manufacture, therefore, these materials must be carefully weighed in exact quantities and surely mixed. For the next step, which is melting. In the glass melting furnace, the raw materials are heated to temperature ranging from 15,000 to 17,000 degrees Celsius, which is 2,700 until 3,100 Fahrenheit, and are transformed through a sequence of chemical reaction to molten glass. Next step, coating. In the final stage, the filaments are gathered, twisted into forming package, and then the process into a textile or other reinforcement forms by weavers or other converters. The lubricants help prevent them from abrasion and breaking. And then the last step, which is drying. Finally, the drawn and sized filaments are gathered into a bundle to create a glass strand that can contain anywhere from 51 to 1,624 threads. The strand is formed into a forming bundle that resembles a spool of thread by winding it onto a drum.
The findings for our topic for fiberglass, which is firstly, the benefits of the products. The benefits of products for fiberglass can be classified into 5 types. First, higher strength. Second, corrosion-free. Third, stable properties. Fourth, good molding ability. And lastly, sustainable. In terms of higher strength, the strength is at the same level as steel, but only at quarter of the density. It is also possible to make weight savings in comparison with aluminium, as the density is 30% lower. The structural profiles have an elastic modulus of 23,000 to 28,000 millipascal. This ensures excellent rigidity and makes the profile particularly well suited to construction tasks that require great strength and low weights. For an example, fitting balconies where a reduction in the weight and installation time is required. Second, stable properties. Fiberglass have high fiber content and a low water absorption capacity, which is only 3%. This means that their properties remain stable throughout the entire lifetime of the product. The third one are corrosion-free. Corrosion-free profiles are resistant to the effects of wind and weather and aggressive liquids. This makes them ideal for use in industry, construction, and offshore installations, for example. Next, the benefits of product are in terms of good molding ability. Fiberglass have an ability to get molded into various complex shapes. This pretty much explains why fiberglass is widely used in bathtub, boats, aircraft, roofing, and other applications. And lastly, the benefits of fiberglass are sustainable. Due to its composition, fiberglass is known for its very low embodied energy. The total energy required to produce a product from the raw material stage through delivery of fiberglass product. Fiber-lined fiberglass profiles are produced using an energy-optimized process that takes the environment into consideration. In addition, the material's excellent durability means that very few maintenance resources are required. The materials can be reused when they are no longer needed, for instance, in cement production. The next findings are the comparison between glass fiber and other materials. In this type of comparison, we compare glass fiber with carbon fiber in terms of three types, which is strength, secondly rigidity and toughness, and lastly thermal expansion. In terms of strength and weight, glass fiber has a strength to weight of 564, while carbon fiber has a strength to weight of 1013, nearly twice as strong. This high strength relative to weight means that manufacturers need to use far less carbon fiber when pultruding a given product. As a result, pultruded carbon fiber products can often get away with significantly thinner cross-sections. This can be simplified as glass fiber has a lower strength compared to carbon fiber. Next, in terms of rigidity and toughness, glass fiber has a less stiff and low rigidity. This level of stiffness, with its relatively supple nature, is a far better choice for applications that entail high flex patterns. Meanwhile, carbon fiber, being relatively rigid, may not be suitable for those applications. Meanwhile, for carbon fiber, the higher rigidity will be allowing manufacturers to meet far more precise stiffness needs. For instance, the silicon tracker modules inside of CERNA's Large Hadron Collider require a degree of stiffness that only carbon fiber pultruded profiles could apply. Lastly, in terms of comparison of thermal expansion, compared to materials like steel and aluminum, fiberglass has a relatively small coefficient of thermal expansion, meaning it won't get significantly larger as a result of temperature changes. If fiberglass exposed to extreme enough variations or if tolerances are especially tight, then fiberglass pultrusion may not be a suitable choice. Carbon fiber has a remarkable property in this regard. It actually has a negative coefficient of thermal expansion. As a result, carbon fiber expands as temperature goes down.
How materials being used or possibility being used. Glass fiber is widely used in construction, civil engineering, commercial and residential products, aircraft, roofing, and sporting equipment. The second one, typical application include the use of glass fibers in polymeric resins for paneling, bathtubs and shower stalls, doors, and windows. And the last one, glass fiber also used as reinforcement in a variety of household items such as papers, taps, and lampshades. Some special alkali-resistant glass fibers have been developed for reinforcement of cement and concrete. For research development related to materials, Glass fiber is a material made up of several incredibly tiny glass strands. Comparable mechanical properties are shared by glass fiber and other fibers like carbon fibers and polymers. When utilized in composites, it is substantially less brittle and far less expensive than carbon fiber, although not being as stiff. Glass fibers are utilized as a reinforcing agent in a variety of polymer goods, resulting in the creation of glass reinforced plastic, which is GRP, sometimes referred to as fiberglass, an extremely durable and comparatively light fiber-reinforced polymer composite material.
Discussion. Our research demonstrates that fiberglass reinforced concrete (FRC) offers significantly better tensile strength and durability compared to conventional concrete, thanks to the high strength-to-weight ratio and flexibility of fiberglass. This material improves stress distribution within the concrete matrix, enhancing its resilience. Environmentally, using waste fiberglass in concrete helps address waste management issues by diverting fiberglass from landfills and repurposing it in construction. This promotes sustainability and reduces the environmental impact of construction. FRC structures have longer lifespans and require less maintenance, further minimizing resource consumption. However, challenges remain for widespread adoption in Malaysia, such as higher initial production costs and the need for strict quality control due to variable fiberglass quality. Compared to other sustainable alternatives, FRC excels in strength but may not be as cost-effective or environmentally friendly as options like recycled aggregate concrete. Further research should focus on optimizing mix design and processing methods to improve cost effectiveness and performance consistency. Additionally, long-term field studies are needed to fully understand FRC's economic and environmental impacts. Conclusion. Our research confirms that fiberglass reinforced concrete (FRC) is stronger and more durable than conventional concrete, addressing the primary research question about its effect on performance. Using fiberglass waste in concrete also reduces landfill waste and lowers the carbon footprint, aligning with our environmental goals. Despite challenges like higher initial costs and specialized manufacturing needs, FRC's benefits improve durability, reduce maintenance, and sustainability make it a viable option for the Malaysian construction industry. This study meets our objectives of evaluating FRC's mechanical qualities and environmental impact, offering practical recommendations for its implementation. Further research is essential to optimize and fully realize FRC's potential in sustainable construction.